So free body diagram of the whole thing, we have 15,000 there. And then we have, I'll call this RA and RC. And I'll put the coordinate system origin here. And now we can set up that table. So the point where the force is applied, the about point, row vector, force, and moment. If we're starting at this force RA, what are the coordinates where that's applied? Zeros, yep. What do you want to choose for an about point? Might as well. And so rho, subtract this minus this, you get 0. The force is RA, x and y. 0 times this minus 0 times that is 0. And now go up to the top. What are the coordinates at that point? 0.5. Right, yep. 0.5, 0.866. The about point is still 0. So there's the row vector. The force is 15,000, 0. So 0.5 times 0 minus 0.866 times 15,000, and yep, negative 12,990. And then over at that point C, the coordinates of C are 1, 0. About point is still zeros. And the cross product gives you positive RCY. So Newton's second law, just add up those. You get RAX, RAY, plus 15,000, 0, plus RCX, RCY is equal to zeros. And the rotational equation, just add these up. Negative 12,990 plus RCY is equal to 0. Okay, so this one tells us that RCY is equal to positive 12,990. And so then plug it in here, and we know that RAY is equal to negative 12,990. And then we only have one equation left. So the first equation that we're going to use to solve a system of equations says RAX plus RCX is equal to negative 15,000. So we'll come back and use that later. And now let's go on and isolate member 1. So the loads on this are, well, we know that the y component of this reaction force we already solved is 12,990 going down. This we don't know yet. This is RAX. And then which member do we want to associate the pin with? Member 1 or member 2? So yeah, according to the convention that I always use, the lower number member at the joint is member 1. So that's where the pin is. And that means that this 15,000 Newton force is applied to member 1. And then there's also this internal load, the force on 1 by 2. Okay, so let's start here. The location, the coordinates where this force is applied are 0, 0. I'm still going to use the about point at 0, 0. This, written as a single force vector, is RAX negative 12, 990. Cross product is 0. And now up here, the coordinates where these forces are applied are 0.5, 0.866. I guess I'll do F12 first. Take the cross product and you get 0.5 F12Y minus 0.866 F12X. And then the last one, this 15,000 Newton force is applied at the same location. So these are both going to be the same. We're going to end up with the same row vector. The force is 15,000, 0. And so 0.5 times 0 minus 0.866 times 15,000 is negative 12,990. So Newton's second law says RAX negative 12,990 plus F12X F12Y plus 15,000 0 is equal to zeros. And then the rotational equation says negative 0.866 F12X plus 0.5 F12Y is equal to positive 12,990. Okay, so these are equations 2, 3, and 4. Now solve that system of equations. You can come talk to me if you can't remember how to plug that into your calculator or whatever, but what you get is, so solve the system, and you get that RA is negative 7,500, negative 12,990, and F12 is equal to negative 7,500 Did we have enough to solve this? We did, right?
Yeah.
Negative 7,500, 12,990. I guess I just didn't write down RCX. Oh yeah, RCX. We can just use. Okay, so, and then RC is, what did you get for that?
What's RC? I don't know.
That's just.
Negative 7,500,
Yeah.
So it's negative 7,500, 12.
Positive 12,990. Okay. And so what this says is on this member, you have a force going, so if you take the magnitude of this force, you get a force of 15,000 pointing along the long axis, putting it in tension. F12, now notice that this force is pointing this way. But remember that that pin also has a force of 15,000 on it. And if you add those two up, you get a total magnitude of 15,000 pointing axially. So this member is in tension 15,000 newtons. Then this one, only at this pin, it only has F12 acting on it, well, F21, negative F12. And, oh yeah, I drew that wrong. So, so this is pointing in this direction. And this is pointing in this direction. So member 2 is in compression 15,000. Okay, so the last step is, so we have these two objects. Here's member 1. And now we're going to think about the coordinate system as having its long axis pointing along the, or the x-axis pointing along the long axis of this beam. And so sigma xx is equal to positive 15,000 divided by the area, which is 0.0025. And what do you get there for the stress?
6 equal to 6.
Okay, and that's pascals. So for member 1, the stress tensor is 6 times 10 to the 6, and then zeros everywhere else. And then the Voigt stress would be 6 times 10 to the 6, zeros all the way down. And this is the one then you could use if you knew the material properties of that bar, of that member. Then you could calculate the strain from this. Member 2 is in compression of 15,000. So again, think about the x-axis pointing along the long axis. Then the xx stress is negative 15,000 divided by 0.0004. And so what do you get for that?
3.75.
Negative, yep. And that's pascals. So the stress tensor for member 2 is negative 3.75 times 10 to the 7th. And the Voigt stress is negative 3.75 times 10 to the 7th, and then zeros. Okay. So those are the states of stress at any point inside these members, except where do we trust them? Where don't we trust them? Near the loads, we don't trust them. So somewhere in the ballpark, so we want to skip somewhere in the ballpark of 0.05 meters at the ends. Really, it would be the diagonal. But it's really not that exact of a principle. It's really more kind of a rule of thumb type thing. The longest, you want the longest distance on the loaded side. So it would be, so if the loaded side is square, you'd really technically want to take the diagonal of it and not trust values that close to the loaded side. It's not that exact principle though. And then this one, we trust these values here, but not close to the loads. Okay, so this was with in a structure where the only internal loads are tension and compression. So next, we're going to deal with bodies that have shear force and bending moments. And the first thing I'm going to do to talk about that is we're going to go back to internal loads. I know, you guys who took statics with me, we've already done internal loads, but we're going to do it again. So, and exam 1 is next week, 1 week from today. And so I guess I'll look at the practice problems and let you know what problems, like it's going to cover everything up through uniaxial tension and compression. But I'll look at those practice problems today and let you know which ones you're sort of responsible for. Okay.